As promised in the previous video, we will now look at some sufficient conditions for integrability. Let R be the rectangle AB cross CD throughout this video. Then, given a function f from R to R, the function is integrable if and only if, given any epsilon, you can find a partition, let's call this partition P, such that UFP minus LFP is less than epsilon. That means you can find a partition such that the upper sum and lower sum can be as close as you want. Let us see a proof of this fact. First, we will prove that if f is integrable, then given any epsilon, you can find a partition P such that UFP minus LFP is less than epsilon. To do this, first notice that f is integrable implies that upper integral is equal to lower integral. But upper integral is the infimum of all upper sums. Therefore, if you take a slightly bigger number, say upper integral plus epsilon by 2, then you can find a partition such that UFP1 is less than or equal to upper integral plus epsilon by 2. Similarly, you can show that there exists a partition P2 such that LFP2 is greater than or equal to lower integral minus epsilon by 2. But lower integral is equal to upper integral, so we can write this as LFP2 is greater than or equal to upper integral minus epsilon by 2. Let P be a common refinement of P1 and P2. Then notice that UFP will be less than or equal to upper integral plus epsilon by 2 and LFP will be greater than or equal to upper integral minus epsilon by 2. Therefore, UFP minus LFP will be less than or equal to the difference between these two quantities, which is equal to epsilon. And thus we have proved one half of this theorem. The other half of the proof is even easier. Whatever be the partition P, we know that upper integral will be less than or equal to UFP. Similarly, lower integral will be greater than or equal to LFP. This is true for all partitions. Therefore, upper integral minus lower integral will be less than or equal to UFP minus LFP for all partitions. But we have assumed that there exists a partition P such that UFP minus LFP is less than epsilon. In other words, given any epsilon, you can find such a partition. Therefore, upper integral minus lower integral should be less than epsilon for all epsilon. As epsilon is arbitrary, this would imply that upper integral is equal to lower integral. But this implies that f is integrable and thus we have completed the proof of the theorem. Let us now show the integrability of a simple function using this result. Let f be the function from AB cross CD to R defined as f of x comma y is equal to x. We will show that this function is integrable. First, let us see what LFP is. Notice that LFP is equal to summation Mij Aij. But Mij in the rectangle xi to xi plus 1 cross yi to yi plus 1 will be equal to xi. And Aij is equal to xi plus 1 minus xi into yj plus 1 minus yj. Now notice that all the coefficients of yj plus 1 minus yj will look alike because Mij does not depend on j. Therefore, we can collect all those terms and sum them together. Therefore, we can simplify this and write this as summation over I xi into xi plus 1 minus xi into y1 minus y0 plus y2 minus y1 plus etc. up to yn minus yn minus 1. And then we can cancel off most of the terms. The only terms that will remain will be yn minus y0. But yn is equal to d and y0 is equal to c. Therefore, this sum is equal to summation over I xi into xi plus 1 minus xi into d minus c. Similarly, UFP is the summation of capital Mij into Aij And as before, we can simplify this as summation over I xi plus 1 into xi plus 1 minus xi into d minus c. Therefore, if you take the difference between the upper sum and the lower sum, UFP minus LFP, that will be equal to summation over I xi plus 1 minus xi into xi plus 1 minus xi into d minus c. Now choose a partition P such that whatever I you take, xi plus 1 minus xi should be less than epsilon. If you choose such a partition, then observe that UFP minus LFP will be less than epsilon into d minus c times summation over I xi plus 1 minus xi. But summation over I xi plus 1 minus xi is equal to x1 minus x0 plus x2 minus x1 plus etc. up to xn minus xn minus 1. As before, all terms except xn minus x0 gets cancelled and xn is equal to b and x0 is equal to a. Therefore, UFP minus LFP is less than epsilon into d minus c into b minus c. That is, we can make UFP minus LFP as small as we want. And thus, we have the integrability of this function. Okay, so this function is integrable, but what is its integral? Let us try to answer this question next. Recall that we had shown that UFP is equal to summation over I xi plus 1 into xi plus 1 minus xi into d minus c. Now we choose a special partition, namely a partition where xi is equal to a plus I into b minus a by n. Therefore, xi plus 1 minus xi is equal to b minus a by n. And thus we can write UFP as d minus c into b minus a by n into summation over I a plus I into b minus a by n. This is equal to d minus c into b minus a by n into na plus b minus a by n into n plus 1 by 2. Therefore, this can be simplified as d minus c into b minus a into a plus d minus c into b minus a the whole square whole divided by 2 into n plus 1 divided by n square. As n tends to infinity, this will tend to d minus c into b minus a into a plus d minus c into b minus a the whole square whole divided by 2. Therefore, the upper integral is less than or equal to this quantity, but we still don't know the value of the upper integral. But using similar computation, you can also show that LFP for this partition will also converge to this quantity. Therefore, the lower integral has to be greater than or equal to this quantity. And this will imply that both upper integral and lower integral is equal to this quantity, and therefore the integral of this function is equal to this quantity. Thus, we can say that this is the value of the integral of this function. So far, we did not have a notation for the integral. We will denote the integral by two integral signs over the rectangle R, then the function, and then we will write dx dy. That's how we will represent the integral of a function. So the integral of x over the rectangle R is equal to d minus c into b minus a into a plus d minus c into b minus a the whole square by 2. Now let us return to some theorems about integrability of functions. Let f and g be two functions from the rectangle to the set of real numbers, and let f and g be both integrable. Then we can conclude that the functions f plus g and cf are both integrable. It's not just that these functions are integrable, the integrals can also be represented in terms of integral of f and integral of g. More precisely, integral of f plus g is equal to integral of f plus integral of g. Similarly, you can also show that the integral of c times f is equal to c times integral of f. Let us now try to see a proof of this fact. I will prove the first statement and leave the second statement as an exercise. First of all, notice that supremum over x of f of x plus g of x is less than or equal to supremum over x of f of x plus supremum over x of g of x. And similarly, infimum over x of f of x plus g of x is greater than or equal to infimum over x of f of x plus infimum over x of g of x. Therefore, we can conclude similar inequalities about the upper sum and lower sum. More precisely, the upper sum of f plus g over the partition P is less than or equal to the upper sum of f over P plus the upper sum of g over P. Similarly, the lower sum of f plus g over P is greater than or equal to lower sum of f over P plus lower sum of g over P. Therefore, u of f plus g comma P minus L of f plus g comma P is less than or equal to UFP minus LFP plus UGP minus LGP. Now notice that we can make UFP minus LFP and UGP minus LGP as small as we want. Why? Because f and g are both integrable. And therefore we can make UF plus g comma P minus LF plus g comma P as small as we want. Thus f plus g is integrable. Further notice that this inequality tells us that the infimum of all upper sums of f plus g is less than or equal to the infimum of all upper sums of f plus the infimum of all upper sums of g. Therefore, the upper integral of f plus g, which is equal to the integral of f plus g over the rectangle R, is less than or equal to the upper integral of f, which is equal to the integral of f, plus the upper integral of g, which is equal to the integral of g. Similarly, using the other inequality, we can show that the lower integral of f plus g, which is equal to the integral of f plus g, is greater than or equal to the lower integral of f, which is equal to integral of f, plus lower integral of g, which is equal to integral of g. The two inequalities together gives us that the integral of f plus g is equal to integral of f plus integral of g. And that completes the proof of the theorem. Finally, we will prove a theorem that gives us a rich class of integrable functions. More precisely, we are going to show that all continuous functions on R are integrable. Let us repeat, if f from R to R is continuous, then f is also integrable. Let us now try to see a proof of this fact. But to prove this theorem, we will need a fact, and we are not going to prove this fact. We are just going to state it. This fact is, if f is continuous on a closed rectangle, then it is uniformly continuous. This is analogous to the theorem that if f is continuous on a closed interval, then it is uniformly continuous. Uniform continuity means that for every epsilon there exists a delta such that norm of x minus y less than delta implies mod of f of x minus f of y is less than epsilon. In other words, although delta might depend on epsilon, it does not have a dependence on the point at which we are checking continuity. Once we have uniform continuity, you choose a partition such that the diagonal of every rectangle in this partition will have length less than delta. If you choose such a partition, then notice that capital Mij minus small mij will be less than epsilon. Therefore, UFP minus LFP, which is equal to summation of capital Mij minus small mij into xi plus 1 minus xi into yi plus 1 minus yi. And as capital Mij minus small mij is less than epsilon, this is less than epsilon times summation of xi plus 1 minus xi into yi plus 1 minus yi. But this is equal to epsilon times d minus c into b minus c. And therefore, we know that we can make UFP minus LFP as small as we want. That is, f is an integrable function.